All right, so coming up now, we've got our LuSTR panel. So I'm here to introduce Harri Vanhalla, who is the Lunar Surface Technology Research Lead for Space Technology Research Grants Program. Dr. Harri Vanhalla is the lead for the LuSTR program element at Space Tech. Goal of LuSTR is to advance technologies for lunar surface exploration and accelerate the technology readiness of key systems. Technologies developed under LuSTR support Artemis and align with the 6 focus areas of LSIC and of LSII. So Dr. Vanhalla has been involved with numerous NASA programs in the past, including flight opportunities, fundamental physics, physical sciences program, messenger, astrophysics research programs, all sorts of wonderful stuff. And I remember when LuSTR was announced at our LSIC kickoff meeting just a few years ago. So very excited to see how those programs, how those awardees have developed. And I'll let Harri take over.
All right. Thanks for that great introduction. Next slide, please. Actually, I guess I can try and turn it. Oops. There we go. I'm very delighted to be here to talk about the LuSTR program, Lunar Surface Technology Research. So as was mentioned, when LSII and LSIC came together, NASA decided to do a solicitation that's really focused on advancing the goals of LSI and LSIC. So it is a program that's based in the Space Technology Research Grants Program, which is one of the programs in the STMT. And the whole point is really to support the LSII. And one of the ways that we do that is really focus on seeking proposals that are relevant to the 6 focus areas that LSII has. Some of the technical characteristics of the program are we're looking for unique, disruptive, or transformational lunar surface technology development. We are in the early stage technology development group, so it is a TRL is typically 2 to 4. And we also do emphasize that instead of just doing technology development without the end goal and use in mind, we do ask people to consider post-award infusion. So not as part of the actual award of developing technologies, but something to follow after the award has been considered. We do have a few eligibility requirements. One of the main points of the STRG, Space Technology Research Grants Program, is that it's focused on US academia. So the submitting organization must be a US accredited university and the PI must be located at that university. However, we do encourage teaming with other universities, industry, nonprofits. And I think most of the awards that we have given out have included these kinds of very fruitful collaborations. These are fairly short duration grants, so 2 years, values up to $2 million. And as I mentioned, they are grants. I have old-fashioned URL for the website. And also if you have questions about LuSTR, you can also email us. All right, this basically shows the current LuSTR portfolio. So it's separated by the year. So we had 2 rounds of LuSTR awards given so far, LuSTR 20 and LuSTR 21. And the years basically reflect the year on which the solicitation was released. On LuSTR 20, we had 2 focus areas that we featured, ISRU and surface power. On both of these, we made 3 selections. So we have 3 awards in both of these areas. In LuSTR 21, we also featured 2 focus areas, excavation and construction, where we made 2 awards, and extreme environments, where we made 1 award. So we currently have 9 active LuSTR projects going on. We also have actually active solicitation that is active for a couple more hours. Today is actually last day that LuSTR 23 is open. And there we actually featured 3 topics that hopefully we'll make awards on in the next few months once we get the proposals in. At this point, we are focusing on the 3 awards that I've circled in the white box. LuSTR 20, as I mentioned, LuSTR is 2-year award. These were awarded in May 2021. So we are roughly entering the final stretch of the LuSTR awards. And the 3 grants that we're hearing from today are the three that are furthest along in their progress. So we are maybe not the quite final results from these projects yet, but pretty close to hearing what they have been doing over the last couple of years and where things stand as they start closing toward the end of their awards. So without further ado, I think I'll turn this podium over to our first presenter, who's going to present results from his project. So let me introduce Dr. Paul van Susante. He's an assistant professor at the Michigan Technological University in the Mechanical Engineering Mechanics Department. He is the founder and PI of the Planetary Surface Technology Development Lab, also known as Husky Works. Dr. van Susante's research focuses on robotic systems for ISRU and construction, and in particular robotic mechanical systems under lunar and Mars conditions interacting with the lunar and Mars surface. He is actively researching, developing, and testing technologies under lunar and Mars environmental conditions for detecting volatiles in lunar regolith, determining geotechnical properties of lunar regolith, conveying and compacting lunar regolith, excavating cemented lunar regolith, excavating gypsum, and extracting water from excavated gypsum and buried glaciers on Mars, applications, as well as developing power transfer via superconducting tether into the lunar permanently shaded regions. So a lot of very interesting work. He is a PI on multiple NASA and industry-funded ISRU projects and with a combined value of over $4 million. And one of these awards is LuSTR 20, one of the first ones we awarded. So Paul, go ahead.
Thank you, Harry. All right, let's see. Cue up my slides. Maybe. Well, it is after lunch, so not everyone will fall asleep in the meantime.
Mitch, we have the slides coming. Yep, he's working on it.
All right.
Nope,
Well, it's been an interesting 2 years.
Do we not have the slides?
The slides are in the ether somewhere. On the moon, I hope not. Anyway, it's been an interesting 2 years.
Do you have a joke for us, Paul?
Press. There we go. On screen. Okay. Let's see. Can we go forward? Full screen. Okay, I'll tell you. All right, next slide, please. So the topic of this LuSTR project was to identify lunar volatiles, but also, while we do that, to detect geotechnical properties. In other words, not only what volatiles are there, but how hard might that be to excavate in the future as well. And to map them, we can't just do point inspections. We want to have sort of a map. And so our idea that we proposed, and that was funded, was to use a cone penetrometer to make spot tests. And every 10 centimeters, we stop, and then we would heat up the probe and then measure the thermal profile. And from that thermal profile, we could then identify what volatiles would be there and how many there are. Just to put it in simple terms, like when you boil water, right, the temperature doesn't change. And then at some point your pot boils dry and then the temperature goes up again, all right? So same principle here. We heat it up, see what the temperature profile is, and if the temperature stays constant for a while, there's a phase change going on, and where that happens tells us what volatile it is, and how long that temperature stays constant tells us how much of that volatile was there. And then in between those cone penetrometer tests, we use ground penetrating radar to see how consistent those results are. You know, if I just happen to find the one little ice cube, I got to figure out if there's lots of ice cubes or I just got the one thing. And so ground penetrating radar can tell us what happens in between our cone penetrometer tests. Next slide, please. This project was divided up in roughly 8 tasks. I'm not going to go into too much detail here, but here you can kind of see there were lots of students and other people involved with this. It's a $2 million project, and so lots of students are involved. One of our big challenges actually was the turnover of students that when they graduate and things like that, to make sure we kind of keep going. I'm going through each of these tasks along the way right now, but I only have 15 minutes to talk about 2 years of project, so I will go fast. Next slide, please. Task 0 was really kind of a support task in a way. We had to figure out all our different test setups for all these different activities that we're going to do. And so part of that was modifying an existing field rover so we could put the ground penetrating radar on there. Another one was building test setups for a trench that you can see at the bottom there. And another one, so we're working on IC regolith, and so we needed to create IC regolith. And so in the summer, that's kind of hard to do, although we get a lot of snow in the winter, the summer doesn't work. So we got a freezer container. But as you remember, it was COVID, freezer containers were hard to come by. Next slide, please. I'm not going to go over why. Anyway, the next task then was to create simulant. We were looking at geotechnical property determination, and using sand or other things is not the same. So we needed to create a proper lunar simulant. However, as much as I love Exolit Lab, I cannot afford to spend $35 per kilogram if I need 35,000 kilograms. So we made our own, basically. We got the ingredients from the same sources they did, and then we made our own, basically. Now, we needed simulant for various different test beds. We had the thermal profiling test bed for the lab scale. Then we had a full-scale thermal profiling test bed because we had to go 1 meter deep, and that's pretty big scale. You know, that cube you see there's almost 2,000 kilograms of lunar simulant in there. Then, even bigger scale, we needed to have this robot with ground penetrating radar do a test, final test essentially, where we had layers of icy simulant and dry layers, and then we needed to detect what was there. We knew what we made. The question is, what we measure, could that correspond to what we made in that case? And that was going to happen at a large test facility that we have at Michigan Tech. And then lastly, we need to test this under vacuum conditions because things behave differently. And so for that, we have Honeybee Robotics to help with us. Next slide, please. All right, simulant production. So we're part of CLASS as well. And so we had some synergy between the different projects that we have at Michigan Tech. And so CLASS, our node of CLASS, was really focusing on creating that lunar simulant. So it has a proper particle size distribution, so we can then use it for proper geotechnical properties. As you can see, again, this was during COVID. And so you need to wear PPE to work with this simulant. This is unfortunately the exact same PPE that people need to protect from the virus. So we couldn't get any. I already had this from Lunabotics one time. I was a judge for that one time. And so I was the only one that had PPE, so it was me shoveling lunar regolith. The students enjoyed that a lot, just gonna tell you that. Anyway, next slide, please. Then for the larger quantity that we needed to fill the large trench, we couldn't do it in-house anymore. And so we partnered, or I should say I contracted with a pilot plant in Duluth who specializes in crushing and making particles to specific sizes. And they crushed the scoria for us because the green spar already came pre-crushed. So with doing that, we managed to keep our cost down to $75,000 for the simulant. So that's, when you do the numbers, $3 a kilogram, which is pretty good. All right, next slide, please. Now, when you make icy simulant, you mix ice in it. But when you're done using it, now you have wet simulant. That's a problem if you want to put it in a vacuum chamber. And so we need to have a way to dry our simulant. Now, if you have small batches, you can just put it in an oven, but when you have 2,000 kilograms of it, that's a lot of load. So we got a drying container, essentially a freezer container that we turned into a heating container. And I made a moondust bakery on the right with lots of trays where we spread out the simulant, thin layers to dry it. Now, why do we do that? Well, because it is very non-permeable. In other words, gas gets trapped in between the particles, and you can heat a big pile, but only the outer surface dries. So to dry it quickly, you need to spread it out in thin layers, and that's what that's for. This is all infrastructure that we needed to be able to do these large-scale tests. Next slide, please. All right, now we're going to get more into the instrumentation itself. Our goal is to identify lunar volatiles, and so thermal cone is an important aspect of that. We need to heat something, and then we need to measure the temperature changes. Now, as you can see, there are lots of volatiles potentially in the lunar surface. But unfortunately, we can't test all of them because some of them are very deadly, and I like my students. So we selected some that we're testing with that were doable, have good representation from a temperature standpoint, and those are the ones we're looking for. Of course, water is the main one. Next slide, please. Now, the methodology that we're using is we have a cone penetrometer that goes in every 10 centimeters, you stop and you heat it up. And when you do that, you heat up the cone, you get these profiles that you see on the top right. Now, one of the parts of the project we had to figure out is how much power do we need? How fast do we need to heat it up? And what percentages of volatiles can you actually measure given those different power levels and things like that? So we have, and this is only just a few of these profiles, we have a whole host of these profiles, and these are done all under regular atmospheric conditions, and we are working on doing the same test now under vacuum conditions. Now, the test results showing over here, as you can see, those arrows show some phase changes which we expect to see. We go from ice to, in this case, liquid, because it's atmospheric conditions, and from liquid to the gas phase. Now, when you do the same kind of thing in vacuum conditions, you would expect to go from just solid ice to the gas phase, sublimation. However, because the low permeability of the lunar simulant, we are actually seeing that there is a condensation stage in between, because initial gas increases the pressure, and then you actually get condensation, which is actually very unexpected. And so that's something that we see and now try to also implement in our models. Next slide, please. Now, the volatiles that we are trying to work with are not just water. And like I said, the previous test was all done under atmospheric conditions, and now we're trying to do this under vacuum conditions. So we've built a unique test setup here that allows us to cryogenically mix volatiles, the lists there: water, carbon dioxide, methanol, methane, ethylene, and sulfur dioxide. Now, the last one is highlighted red because that one's dangerous in the ppm range. And so we're first doing everything with the other ones, and once we got the process down, we're going to do the sulfur dioxide one. Now, what we have created here is a totally cryogenically cooled process, basically, where we pre-cool the liquid nitrogen, we pre-cool the regolith, then we pre-cool all the volatiles, but we don't want to mix liquid in there, or gases. So we are actually creating volatile snow, a liquid nitrogen cooled volatile snow, and then we mix that in with the pre-cooled regolith. Everything is still being cooled at liquid nitrogen temperatures. Then we put that mixture in a vacuum vessel, as you see at the bottom there, in which we have a heater and thermocouples. Then we close the lid, create a vacuum, we vibrate the system so we get compaction going, and then we use the heater and measure the thermal response of these systems. And we do that for different percentages of these volatiles so that we get all those thermal curves for the different percentages of all of these different volatiles. So this is still ongoing work. There was a lot of stuff left to do here, but we now have it all working finally. It's been quite the work. We found out that a lot of steps here needed refinement. When we thought we had it, something else still needed to be improved, but we finally have it. Next slide, please. All right, so the cone itself, right? This is the part that goes on the cone penetrometer. It measures geotechnical resistance basically going down, and we are measuring the forces while we do that. That's for the geotech piece. Now, in this case, for the thermal part, we need to have a heater, and in this case, several thermocouples on the cone itself. When we create thermal profiles you just saw, we have those thermocouples in the simulant, but in this case, we need them on the cone. And so this is what we have here. And so we needed to go through several iterations of this cone before we had it all working. There were some reliability issues, because you can imagine if you hammer your sensitive instrument in the ground with a cone penetrometer, things tend to break. And so we finally got it to the point where it works and it actually measures these profiles that we're talking about. Next slide, please. Now, this cone is now being tested. And so we see some profiles, like you see at the bottom right. So this is done in a box of lunar simulant in a small vacuum chamber. This is cooled to minus 80 degrees Celsius and water doped, in the sense that we mix certain different percentages water in there. And then we start heating the heater element of the cone and measure the thermal response. Now, because this is in a lab, we also have some thermocouples that are not on the cone. But both of those measurements here you can see in the graph on the bottom right. So you can see phase changes in the slope of the heating curve because we're heating at a constant rate. And so anytime there's a phase change, you see a change of that slope. Now, there's different things that we can measure from this. We're still calibrating a lot of details on this, but you can clearly see there are phase changes. And what we're trying to figure out is, okay, if I see this change in my curve, what percentage of volatile does that correspond with? And that's why we need those other data sets. Next slide, please. Now, on top of that, once you have a, let's say, measurement on the moon, you don't know what actually was there. And so you have a mixture of volatiles, and just like you have inversion problems on Earth when you have, let's say, seismic graphs, you need to do something similar there. So what mixture on the moon gave us the response that we measured? And so to be able to do that, we need to have a good model that mimics the physical changes that occur in the lunar simulant. And so that's what we have here. So that modeling is still ongoing, an ongoing effort, especially since we saw 3 phase changes instead of 2 phase changes that we expected. This became a little more complicated than we originally thought, as with all research, I guess. But anyway, so this is still ongoing work. As you can see at the bottom left, there are a lot of steps that need to be correctly modeled to get the right answer. And we're very close, actually. Next step, please. Geotechnical properties, all right? So 2 minutes. All right, I got to go a lot faster. Next slide, please. So geotechnical properties are done with the same cone, but with different sensors. So we have a load cell at the bottom, and we measure the impact load and the resultant load at the bottom as well, and that we can figure out impact versus response. Next slide, please. We do this test in pre-made layers. We have built a special test bed to known compaction, and then we can measure what the response is. Next slide, please. Now, we were interested in ice, and we were interested in to see if we mix ice particles in there, what that effect is. And so you can see on the left, those blue layers are layers that have ice in them, whereas on the right, or let's say the middle picture, that's a compacted layer without any ice. And so you get an increase in strength going down, whereas if you have ice layers, you actually see a reduction in strength in those layers that have ice. Next slide, please. Task number 5, the ground penetrating radar to figure out what happens in between the cone penetrometer tests. Next slide, please. So we modified our field rover to have 2 simultaneous ground penetrating radars, 500 and 1000 megahertz, and we field tested that on what we call the stamp sands, which are literally thousands of acres of mining leftovers of purely crushed basalt, just like the moon in many ways. Next slide. And we buried targets there in the sense that we were looking for ice. So let's bury a block of ice in the basalt and see if we can see it with radar. We also buried CO2, dry ice, like ice cubes and rocks to see if we can see the difference. Next slide. And this is an example of a radargram that you get. In this case, we don't just have a line, we have a grid. And we had some issues with the grid because you're supposed to get an X marks the spot, literally like the white arrow at 0.5, the white X. But you can see the data was offset for the different patterns. That's because our grid patterns weren't exactly aligned with the grid, the black grid that we have in the computer. Next slide, please. Now, to calibrate things, can we see ice? Can we see rocks? We did a lot of calibration tests. Lunar simulants, again, we buried a clean, nice target, and we see what kind of response do we get. Again, to get a data set to see what does GPR data of ice look like versus basalt rock in lunar simulant. And so we've got a whole bunch of data showing that, and you can see in the radiogram on the right, there you can clearly see where the target is. The other thing that's really important for GPR is the actual wave velocity to it, and we need to calibrate that to interpret the results properly. So we bury it at a known depth, and then we can figure out what that velocity is of our simulant. Next slide, please. Now, to make sure we can interpret our results with the stamp sands as well, the field data, we needed to compare the simulant to the stamp sands, and so this is a test setup to measure the different velocities in those different materials. Next slide, please. Number 6, in this case, our whole integrated test setup, we are using the Viper Z stage that was made by Honeybee Robotics. You can see it in the right figure there. We built it or I should say Honeybee built it, shipped it to us, we attached the cone to it, and we have our fully working system. Next slide, please. Then we wanted to test the full system in the field, like I said, with our box. Next slide, please. We needed to reduce our amount of simulant a little bit, so our box was 2 zones instead of 3 zones, but we were all ready to go. Next slide, please. And then we were going to build it over here. We had built the system, the trench was ready to go. We had our 25,000 kilogram of simulant. Next slide, please. You can see the box was built. We were all ready to go. Next. And then we had no winter. The black line was how much ice was on the lake. Versus the red line, which is the average here. It was 51 degrees in February. So we were not able to do our outside test, unfortunately. So we got a no-cost extension so we could do it next year, which hopefully will be a cold winter. I know it's strange to hope for that. But anyway, next slide, please. Then we did do a fully integrated system test with the whole rig and everything. You can see we get depth data, we get thermocouple data, we get impact data, all that stuff. So the system all works. Next slide, please. And to make sure we have some data to the full depth, we made our robot fly, and we lifted it up over our sandbox. Unfortunately, this was too tall for our freezer container, which is why we needed to do this outside in the first place. So this is not with ice, but it does give us a nice, you see the center graph of different layers that were created, and then the cone penetrometer response in the center, and then the calculated geotechnical properties from that data all the way to full 1 meter depth. Next slide, please. Last task, testing in the vacuum system at Honeybee Robotics. Again, that's going to happen next year because currently the Viper flight project is using the chamber time. So next slide. And so with the no-cost extension, we still have some work to do. We expect to finish it successfully next year, assuming we have a good winter. And I think that's all we have. Next slide. Thank you very much. This is a very high-level discussion.
Do you want to take a question now before we
yeah,
get
we
to,
have
do we have
5
time?
minutes of questions.
2 minutes, okay.
Yeah.
So the first question on here is, do you know how your lunar simulants compare to the market? Have you considered giving LSIC a sample so they could independently evaluate it for you?
We have sent our simulant to Johnson Space Center. They have a sample right there.
Okay.
And so we also have compared our simulant on many different metrics as well, and we're about to publish a paper on it. So what we care mostly about is the geotechnical properties. And so the particle size distribution and the mineralogy hardness are what really matters there. And so we've got basaltic simulant as well as green spar, which is the same ingredients Exolit uses for theirs.
Okay, thank you. And then the second question is, was your lunar simulant ground to a uniform grain size, or did it incorporate varying grain diameters and heterogeneous clasts?
That's a great question. So since we are using 3 ingredients, the green spar 90, green spar 250, which come already pre-ground, those have fixed particle size distributions. And then we have a third ingredient, which is our New Mexico scoria, which we crush to a specific particle size distribution. And so we mix those 3 to match the particle size distribution of the Lunar Highlands simulants, Apollo 16, 17, I believe. But anyway, that data is available, and so our particle size distribution is pretty close to that. Now, the minerals are not equally distributed over all the particle sizes. So the behavior might not be 100% correct in that sense. But geotechnically speaking, the packing density is what matters most for our resistance. And so the size of the particles and the shape of the particles are more important than the specific mineral for most of our tests that we do.
Okay, thank you very much.
All right, thank you. More questions, come find me.
All right. So next in our docket is Dr. Rahman. Is he online? All right, very good.
Yes.
So I'll just give a brief introduction. The PI for this grant is Ahsan Shorjuri, but he's not able to be with us today. So MD Rahman has kindly agreed to present the results of this particular LuSTR project in his stead. So Professor Rahman is currently an assistant professor of aerospace and mechanical engineering at the University of Texas at El Paso. Prior to joining the University of Texas at El Paso in 2018, Dr. Rahman has worked as a postdoctoral associate at Massachusetts Institute of Technology. He received his PhD in mechanical engineering from Drexel University in 2016. He has 2 published patents and has co-authored 14 journal articles and 60 conference publications and presentations. Dr. Rahman is currently working on surface engineering and advanced diagnostics of interfacial phenomena, fluid dynamics and heat transfer, in situ resource utilization, advanced thermal management schemes for hypersonic air vehicles, and digital engineering. Thank you in advance.
Thank you. Thank you, Harri. Good afternoon, everyone. So this LuSTR project, so this project is mainly focused on our developing advanced thermal mining technology that has the capability to collect with the lab scale prototype of like 1 kilogram of ice collection in 11 hours. In comparison to the moon collection, this is like 9 tons per year on the moon for this small scale lab scale prototype. So this project is mainly divided in like 3 major components into it. So one is like comparing the existing technologies for the extraction, that is the thermal drill and capture tent, and then starts our novelty, that is once we create the vapor, what we are going to do with that, because it has a very low pressure condition. So we came up with the idea that why don't we throw a lot of electrons on the water vapor molecules and then knock off one of the electrons from the water vapor so that they can become the ionized, as you see in the left picture. So once they become ionized water vapor molecule, and then transportation is very easier, because we can put an electrode, negatively charged electrode, and bring the positive ions to the cold surface where we want to recapture them. And that's what our third system, that is, we want to recapture the incoming water vapor that contains a surface electrode and a very cold surface to the vapor. So for this very cold surface, we are developing a cryogenic heat pipe. This is additively manufactured microscale structure geometries that contains liquid nitrogen as the cryogenic fluid, and these are works on the thin film evaporation technique. So the idea was that the water vapor is going to come and release that heat to the liquid nitrogen inside the heat pipe, so that can reject the heat. So this nitrogen is going to take that energy, is going to become the vapor. So it's going to go to the condenser section and release that heat to the ambient. So once it releases that heat, it's going to become the liquid nitrogen and come back to the evaporator section through the capillary action without requiring any pump. So we are developing this cryogenic heat pipe at UTEP here, so with a lot of experiments. And the final part of this component is that as we continuously collect ice on the cold plate due to the low thermal conductivity of ice, we'll start losing the heat transfer. The heat transfer will degrade. So we developed an idea that we'll put a thin film heater in between the ice and our cold plate. So it's eventually is going to be cold all the time. And when we collect enough ice block so that we can turn on the heater for like intermittently for a matter of like milliseconds, so we can create a vapor lubrication layer between the solid and ice and the cold plate, so that due to the moon gravity, it can delaminate from the cold block and fall on the container. So this way we can continuously use that cold plate and continuously grow our recapture our ice on the cold trap. And final component of the project is like this transforming this lab scale prototype to the scale-up analysis. For that, we have the industrial partner who is helping us to do all the analysis in this part. Now, this project starts with the Characterization of thermophysical properties. The first part is the specific heat. On the left, we have the STA, and we use that STA to measure the thermophysical properties due to the because for the IC regulated mixture at the cryogenic vacuum condition, we don't have enough data to use them for the model. So we started getting this data here at UTEP. So the middle plot, it shows the specific heat as a function of temperature for the dry regolith mixture. We are using two different regolith. One is LHS1 and one is the LHS1D. As you see from this plot, the red one and these blue lines, they are with the considering the experimental uncertainty, there is not much difference between their specific heat up to the cryogenic temperature. And these are compared with this dotted line. Those are for the Apollo data for the lunar regolith. So these are like quite good agreement with the literature. So on the right, now it's time to mix with the water. So on the right, we have the specific heat as a function of temperature for the mixture of like IC regolith with the water. So this results is for like just representative for LHS1. As we see that below 250 Kelvin temperature, there is no, the addition of ice did not have change any value for the specific heat for the LHS1. The next is the thermal diffusivity. So for the on the bottom left, we have the apparatus, which is laser flash apparatus, which we used to measure the thermal diffusivity. And on the right, we have the thermal diffusivity as a function of temperature for the lunar highland simulant LHS1 and 1D. And two different conditions we tested. One is the 90 kilopascal, which is our atmospheric pressure here at El Paso. And we have LHS, the test on under the vacuum conditions. So the squares and the triangles, they represent the squares represent the pressure condition, and triangles represent the vacuum conditions. We have two different colors. One is the red is for LHS1, blue is for LHS1D. And we see that the red and the pressure, atmospheric pressure and the vacuum condition, they have a drastic difference in their thermal diffusivity value. This is due to because the atmospheric pressure we created using the helium, and it has a significant contribution in the heat transfer. However, when we calculated using this thermal diffusivity and the specific heat, we calculated the thermal conductivity. We see that at 1 Pascal pressure, our measured thermal conductivity for the IC regolith mixture is 2 orders of magnitude as compared to the Apollo samples. The next is our creating a simulator, mainly to create a simulator so that we can produce enough vapor sublimation to collect 1 kilogram of ice in our lab. So we tested these experiments at 5 × 10⁻³ torque pressure. We used 2 different simulators. One is the radiative heating. We have like a ceramic heater sitting at the top, and we have IC regolith mixture inside this container. So we give the heat and we create the sublimation. On the next picture, we have the conductive heating. So it's like kind of thermal drill simulator. You have a cylindrical heater. We heat the outer body and then heat up the IC regolith mixture and produce the vapor. So we are comparing the results for both systems because we want to choose for which one we'll be using for our prototype experiments. So on the plot here, we are showing the sublimation mass flux as a function of the power for both the thermal drill and the radiator. So we used 3 different percent of water. One is 4%, 6%, and 8% of water. So as we see that for comparison at 20 watt, we see that the thermal drill sublimation mass flux has very high value as compared to the thermal the radiative sublimation. However, these are tested at nearly at the molecular regime, and we know that MLIs work better below these pressure conditions. So our next works, we want to address that going even below this pressure condition, and then comparing these 2 methods, and so that we can do a better job in the apple-to-apple comparison. Once we create the sublimation, our next job is to demonstrate the vapor, create the vapor ionization, and then transport it to the cold plate. So we are implementing 3 different mechanisms here. One is the left. On the left, you see the DC method, where we have the IC regulated mixture, which will be in a container and sitting on the in this cryogenic TVAC, and we are using a hollow cathode as our DC electron source. Is going to throw a lot of electrons to the vapor molecules, sublimated vapor molecules. And then we are using 9 probes. Those are negatively biased so that they can attract the ions and give you the answer for the ion density you created for a particular method. So this is the DC method. And then in the middle picture, we have the RF radio frequency electron source method, where the electron can have multiple passes so that they can increase the ionization rate, the collision frequency and ionization rate for the vapor ionization. And the very right, we have the magnetic trapping. So we are using a DC electron source. The problem is the DC electron source, once you throw 1 electron, is going to have a 1 pass. So by using the magnetic trapping, you can create like a helical motion for the electrons, so that you can create the collision frequency of the electrons and knock off more electrons from the water vapor and increase the ionization rate. So we are using all 3 methods for comparison, and which one we expect that the magnetic trapping and the DC, the very right one, would give us the highest ionization rate based on our analysis. And the very top, we have the top right, we have the representative data for the percent ionization as a function of power, 3 different power for our radio frequency method we use. So we are seeing that there is like a linear trend with the given power and the number of ions you can produce using this method. And the final part is the ice collection. So once we create the ionization, then we'll be transporting them to the cold trap by the surface electrode, and then create a very cryogenic cold condition, collect the ice, and then delaminate it. So for this method, we are using 2 different heat pipes. So one is the additively manufactured heat pipe, and the other one is the conventionally CNC machine manufactured heat pipe. So this section is going to contain the evaporator section, condenser section, and then integrated section, and the ice collection. So this is our result from the evaporator section, which is the ice collector. So the vapor is going to come land the heat onto this evaporator section. This cryogenic liquid nitrogen is going to take the heat and then collect the ice outside of the heat pipe. So to test that, which type of things, these are like different type of structures. Basically, I think we are the first to run the experiments with the cryogenic fluid, and that it will be manufactured this thin film evaporation. So these data are not available. So we developed the experimental facilities. We are printing the samples and then testing them. So we are testing different variations in the samples. As you see in this picture, the diameters are different, the spacings are different, heights can be different. So we need to optimize that. However, with some analysis and then running some experiments, the experiment data is here. Y-axis is the heat flux as a function of the wall superheat for these the structure surfaces. As you see that using the additively manufactured samples, we can significantly increase our capability of the heat pipe, which can or the heat absorbing capacity during the ice collection, which is quite significant, as we promised compared to what we promised in our proposal, and we are getting very high value for our evaporator section. And once we get a very good evaporator, then we'll have to match the condenser section. So similar way, we ran several different condensation experiments. So here we tried to get a lot of literature information for the gaseous nitrogen condensation. However, the film-wise condensation for gaseous nitrogen on these microstructures and everything, at least to our knowledge, is not available that much. So we used our experimental high pressure experimental facilities to run those cryogenic condensations on using these novel structures, and And the results are presented in here for the heat flux as a function of degree of subcooling, how much subcooling you need to create so that the radiator needs to create so that you can have active condensation, liquid condensation for the nitrogen. And as expected, what we proposed by this yellow line, that is from our analysis, that okay, we'll be needing that much of condensation capacity, and with the structure, additively manufactured structures, we see that quite a significant increase in the heat transfer capability for our engineered structures, even for the condensation. Now, finally, the ice collection. So we ran like several different ice, all combinations of sublimations, combinations of degree of subcooling. On the very left bottom, this is the experimental facility test setup. This is just for the ice collection subsection of it. And then we have, because we want to continuously delaminate and collect ice, that's what this picture is showing, that we can have this continuous ice growth and then also the delaminated ice. And the next video is showing the time lapse of the continuous ice collection on our cold plate. And finally, at the very right video, this is like a snap of turning on the heater and delaminating the ice from the core surface. So in this one, currently we are using off-the-shelf thin film heater, but our prototype will contain our custom design thin film heater with a very high capacity micro scale, length scale, and like kind of like 1 millisecond to heat up create the isothermal wall on the heater. Okay, so the results are presented in here. The figure shows the ice collection rate as a function of degree of subcooling, and all different color represents all different sublimation rate. And what we see that the experiment which we really needed for that, what should be our cold plate size, and what should be our degree of subcooling, and how much heat we need to remove for our prototype. As we see that we were able to get a very high sublimation rate, and with a very high ice collection rate, around like close to 30 gram per hour ice collection rate at a degree of 90-ish subcooling, and percent of ice collection here is like around 63%. The remaining task for this LuSTR project is the developing and creating the prototype and showing that all these subsystems, what we have seen so far, that they're integrated and they can really work together and collect the ice of our promised 1 kilogram in 11 hours. So right now we are developing the cold plate and the heat pipe. So we finished all our calculations for the evaporator section, wick section, condenser section of our heat pipe, that additively manufactured micropillar geometries. And once we develop this one, then we are also adding our thermal drill simulator so that it can produce the vapor. Yeah, I think last, yeah. So thermal drill simulator create the vapor, and then use the DC plus magnetic trapping to bring the water vapor to the cold plate, and this cold plate will collect the ice. So that is the remaining task for this project. And finally, the major impact of this project is definitely the success of the results and everything, getting novel data. Those are very good, but we see ours in the academia, we see our success is our students. This is a list of the students who are already in the job, who has worked in this LuSTR project for the last 2 years, and they're already in different industries, academias, different internships out of which is the outcome of this project. And more students are still working together in this project. So the published, we were able to get around 15 articles in the last 2 years as an output of this project. I think that concludes my talk.
All right. Thank you.
Thank you.
So we have 3 questions, if we can get to them. The first one is, given a vapor pressure difference inside versus outside the hemispherical capture chamber, how would you get a ground seal with an irregular rocky regolith surface? Yeah, good point.
I'm sorry, say that again.
Okay, sorry.
Yeah, sorry.
I got lost in the middle of it. Given a vapor pressure difference inside versus outside the hemispherical capture chamber, how would you get a ground seal with an irregular/rocky regolith surface?
Good question. We have not started that one yet, so I think we'll leave it for our when we'll be working with our. We already started working with our industrial partner, so that we can add that in our scale-up analysis.
Okay, the next one is how big of a radiator would your system need to freeze 1 kilogram of water per 11 hours?
So right now we are not using any radiators. So that's what we showed, that we'll be using the thermal drill, because we found that the thermal drill gives us a very high sublimation rate, and to match our collection, we need the bunch of radiator simulator. Sorry, the drill simulator. Yeah.
And the final one is, what is the density of the ice captured on your plate, on your cold plate?
Very nice question. We experimentally saw a little bit of difference. So at 10⁻³ torr pressure condition, we measured at roughly in the order of 100 to 200 kilogram per meter cube. However, by changing the pressure to 10⁻² torr, we were able to get around 900 kilogram per meter cube density.
Thank you very much.
Thank you very much. Thank you.
Good to move on to the third presenter, Phillip Lubin is online.
Yep. Can you hear me okay?
Good. All right. So just a few words of introduction before I turn it over. Phillip Lubin is a professor of physics at the University of California, Santa Barbara, whose primary research has been focused on studies of the early universe in the millimeter wavelength bands, as well as applications of directed energy for planetary defense and relativistic propulsion. His group has designed, developed, and fielded more than 24 ground-based and balloon-borne missions and helped develop 2 major cosmology satellites. His group has worked on applications of directed energy systems for both small-scale single-launcher solutions as well as large standoff systems for planetary defense, and on applications to allow small interstellar probes to achieve relativistic speeds for the first interstellar missions. He's a co-recipient of the 2006 Gruber Prize in Cosmology, along with the Kobe science team for their groundbreaking work in cosmology, as well as the 2018 Gruber Prize in Cosmology, along with the Planck science team for their determination of fundamental cosmological parameter. He has published more than 450 papers, and we're excited to hear Professor Lubin talk about Moonbeam.
Okay, thank you. I hope you can hear me okay. Apologize for not being there. I have a NASA site review on Wednesday, and it wasn't really possible to get back in time. I want to give you a quick overview. It'll be a fast pace, and feel free to follow up with questions later. My email is listed here. Also, if you're interested in our work, you can find our website with a lot of information, and you can look us up on ResearchGate.
Phil, can you swap your display feed if possible? We're seeing the presenter view.
Yeah, okay, that might be hard. Not quite sure how to do that.
Yeah, I mean,
is there a
display duplicate, looks like,
or not?
Yes, that's good.
Okay. All right, great. So we're in finishing up year 2, and there's a lot of accomplishments here, which I won't bore you with the details of, but basically the system works quite well. We have a laser efficiency of about 50% electrical photon, 1 kilowatt per kilogram is already obtained. On the PV side, on the photoconverter, it's tuned for the laser wavelength. We're currently getting around also a kilowatt, except electrical out per kilogram of LPB, but we have a path to much higher density using thin film, and I'll talk to you about that. There's a lot here. We don't have time for a full discussion, obviously, in 15 minutes. This is part of a larger path that we're looking at of using large-scale directed energy for many applications, and so we consider this to be a kind of a low-hanging fruit to be able to beam from a mother some sort of craft into a PSR rover, which is what we were asked to look at. In this case, the distance is quite short, about 1 kilometer away. Long run, we are looking at much more ambitious goals. End-to-end efficiency currently is around 15%, and we think that can be pushed to upwards of 25 plus. So we'll talk about that. We're also working with some CLIPS groups to see about a demo. As I mentioned, this is part of a long-term program for our group. We've been working in this area since 2009. And in the long run, we hope to have vastly higher capabilities. This is a scalable technology. Unlike many, it comes from basically hand size to as large as you want because it's a parallel process. Okay. In terms of spot size, so this is a mission specific issue. We're currently running at 976 nanometers on the laser side, and we chose multi-mode versus single mode. We use both in our laboratory. We produce almost all of our own photonics in the lab. On the left-hand side, I show spot size as a function of target distance. Here's 1 kilometer, 10 kilometers, 100 kilometers for single mode. This would be using our phased array technology. What we're using for this program is a multi-mode system, which is easier to implement, lower mass, and again, spot size. So this is 1/10 of a meter. They're both the same scale vertically. So this is 10 centimeters. Again, this is the target distance in kilometers. This is 1 kilometer. So the various lines here, the blue is the spot size. So ignore the flux for the moment, which is red. The various lines here are for different optical sizes from 5 centimeter optics, about 2 inches, up to 40 centimeter optic. We're concentrating on a 10 centimeter optic, which gives us about a 24 centimeter spot a 30 centimeter spot at 1 kilometer. Running multi-mode, we go single mode, we get a 24 centimeter spot at 10 kilometers. Mass is quite low, as I'll show you in a bit. Okay, the basic idea is you have a server and a client topology. So the server is the side which provides the power, the client, the one that uses the power. In our case, the power is sent into a rover, and inside the rover is a warm box that keeps the electronics and batteries in the rover warm. And we have both a thermal component as well as an electrical component of the light. So we harvest both electrical and thermal. Okay. So this is a 400 watt handheld version. This is a 300 watt. They're both at about a kilowatt per kilogram. That's a kilowatt optical, about 50% efficiency for both. They're both very reliable. They can last for tens of thousands of hours if treated properly. And we do almost all of our own work in the lab in terms of building lasers, fibers, etc. These are some pointing systems that you'll see used later. Okay, on the client side, again, we have both an electrical component as well as thermal components. We treat the thermal component like a battery. Phase change material, for example, actually has similar energy density to lithium batteries in terms of watt hours, in terms of energy per unit mass, and then radiators, etc. It's a fairly complex assembly. Okay, first generation system that we built. This is approximately 2 inches in diameter. This will produce a 60 centimeter spot at a kilometer. Very compact, very reliable. The laser does not move. The targeting system is a full 4 pi capable targeting system, so you can shoot up, down, sideways, whatever you want. The laser stays stationary. This is second generation unit that we built. This is full scale, 10 centimeter aperture. So about 4 inches in aperture size. Here's the output aperture, laser shown over here with a collimator. There's a full targeting system on board with a 2 pi, greater than 2 pi wide field of view camera to look for the targets. And then the target in this case is a photoconverter. Okay, here's a little demonstration I'll show you. There's a rover that's going to move back and forth. It's at nighttime, so you'll be able to see it in a moment. Here we're running at low power at slightly shorter wavelengths, 888 nanometers. And you'll see here This is the unit in the evening. The rover is over here. You'll see blinking lights for target locking. So the rover's over here. It'll soon be blasted and then move across the outdoor area. And you can see the rover moving over the side. The camera picks up the rover and then we'll lock again onto the target. Okay, so you can see it being blasted at that point. Okay, this is the third generation that we built. Looks similar to second, but it's more refined. This is suitable for full 1 kilometer targeting. It's has a mass of about 2 kilograms, not including the laser and collimator. About 5 kilograms complete with laser and collimator. It's optical closed loop, as well as RF communications and optical communications. There's also an aiming laser, which is over here. I'm not sure if you can see my cursor or not. And there's a narrow field targeting camera over here. I'll just show you. Yes, it does move and works fine. It's not suitable for cryogenic application. We would have to change some things to make it suitable for use on the moon, but it could be flown with some additional work, which wouldn't take that much to put it into a flight configuration. Okay, beam pattern on targets, relatively good. We spent a lot of time working on the beam targeting, getting the beam on the photoconverter to be quite reasonable. We're also using maximum power point tracking on the electronics. It's working out pretty well. And I apologize for the rapid pace here. We've gone through 3 generations of rovers now. This is somewhat more suitable for use on the beach in Santa Barbara or use in a lunar environment. It's works well. Standby power is less than 1 watt, and you can shut that down to almost 0. The tires, obviously, you wouldn't use these since they're air inflated on the moon, but you can make something that would work. Okay, here's a silicon photoconverter array, and here's an indium gallium arsenide photoconverter array. All right, here's a unit in the lab. You can see the rover over here with the photoconverter, and here's the laser and the beam director, which can hit anything in the room. Here's the target. I'll show you a little movie just to show you that it works. You can't hear the sound, but if you watch the fan in a moment, the beam will go on. Light goes on, fan goes on. Okay, so power is being sent over. Here's a 3rd gen system with targeting. This is the full 2-pi monitor. You can look all around you, find multiple rovers. It finds one over here. If you play a movie, you can see lights flashing and targeting going on. Moves around, finds target, and then hits the target. Anyway, it works. Okay, it's just lab testing at full power. You can kind of see the communication scheme going on. Again, this is designed for essentially an unlimited number of rovers that may or may not need energy. If they don't need energy, then we don't provide it. So we lock onto the target. Works well. Okay, laser photoconverters, we spend a lot of time working on both silicon as well as indium gallium arsenide. We've tested many hundreds of cells and built our own arrays. We're working at two outside vendors. One is Boeing Spectra Lab on their InGas. We have several hundred cells from them. It's part of a collaboration. And then we're working with Microlink on thin film, extremely low mass photoconverters. Lots of testing in the lab. I won't bore you with all the IV curves, but the efficiency for silicon is actually pretty good. We're getting about 36% at 888, 32% at 976, and 28% at 1064. And these are really not even optimized. This is working remarkably well. In theory, we should be able to get about 60% at 976. And we're working with both Boeing and Microlink to get there. We have measured them, so I'll show you some of that. Again, we measure, in our lab, we have lasers of all kinds of wavelengths. 3 that we use for this program are 888, 976, which is baseline, and 1064. 1064 is run in single mode, 976 is run multi-mode. We literally have tested hundreds of thin film and thick film or thick photoconverters in InGas, and we get awarded 35% or so. These are not optimized yet. We should be getting more like 50%. So we're working on that. Okay, here's just full targeting. This is using silicon, 14% effective throughput. There's no MPPT on this one. Then with InGas, we get about 27% throughput. These you have to cool because we put quite a bit of flux on them. So in this case, the cooling would be used for heating of the thermal battery, the phase change material. The microlink devices are extremely thin film. These are about 50 grams per square meter. Most of that's dominated by the backing structure, which is a kind of a Kapton. So in theory, we could get to about 20 kilowatts electrical per kilogram, which would be quite remarkable for a photoconverter. So that's coming in the future. Working with Boeing on increasing their quantum efficiency, conversion efficiency, we get about 45% for the best cells. It really should be up here more like 55 to 60%. So some work going on in that area. We developed our own maximum power point tracking, so we can track at about 10 kilohertz rate, which is much faster than we need. Very efficient. It's about 98, 99% efficient. A lot of work on thermal management. It's nothing major there. Running out of time. We did do a long range test, a 1 kilometer test at Dahlgren as part of the Naval Research Lab for a different program, but it was useful as part of LuSTR. That worked well. We're working on the thermal battery component. You get pretty good energy per unit mass. This is water is actually pretty good. You get about, in terms of the heat of fusion, you get about 300 joules per gram. Wax is around 200 to 300, and lithium is actually about 400. Okay, as part of the program, we also developed a novel system for maintaining warmth within the rover.
You've got 2 minutes.
I got it, right. We call it surviving the lunar night because you can actually use it for surviving through a 14-day night without having any external energy sources. We built it, it works, and it's mostly an undergraduate project. So we've completed most of the goals. We're still working on some of the goals, so we're requesting an NC to continue. The program, I'd say, in general is going quite well. We're quite happy with the progress we've made. Okay, lots of undergraduates as well as researchers in our group. Co-investigators include Boeing, Microlink, Enlight, and Intuitive Machines in terms of looking at possible flights. We've had a large number of students, and in this program, we've had about 50 students working on LuSTR. So that's worked out incredibly well. Students love it. Potential impact in fusion. There's good synergy with our phased array work where we could run single mode. So for single mode, you can go much further. So it is possible to transfer single mode over 100 kilometers. Essentially, there's no atmosphere to worry about, so very little loss. And that's something to think about. So then finally, we compared wires to directed energy solutions. And this is an interesting trade space. If you're interested, please talk to us about this. We spent a lot of time doing optimization studies. Obviously, in a mobile environment, as we were asked to solve for Moonbeam, the LuSTR program used directed energy because you want to hit multiple targets. But even large distances compare well using directed energy versus wires. And that's shown in this plot. Okay, I'll stop there.
Okay, thank you. So we have a couple of quick questions here, and then we'll go to a little bit more with the panel. If a technology provider wants to be compatible with your power beaming, what do they need to keep in mind when they are designing their technology?
So for the power provider or for the client side?
It says provider.
Yeah, okay. So for us, we basically just take electricity in. So if you hand us any reasonable form of electrical power, we can take that and then convert it to power the laser side. There's nothing unusual there. If the question was really meant on the client side for the rover, we would want to work with a manufacturer of the rover to look at how to properly thermally engage the system, both to harvest the thermal portion as well as the electrical portion, and how to keep things warm. we not only believe, we've shown that we can keep systems warm during the lunar night if you design them properly.
Okay, there's one that just got upvoted. Are there safety protocols astronauts will need to keep in mind if working around this power beaming technique? If so, do you begin to define them?
Sure. So lasers, like any bright light, including LEDs you buy in the store, often have a sign saying "Do not stare at beam." Ours are invisible to the human eye, so it makes it a little bit more dangerous. The simplest solution, to be honest, is if the astronauts are outside, then they have to have a helmet on. If they have the helmet on, you coat the helmet with a reflection coating tuned to the laser. And essentially, it's like wearing laser glasses, except you never know it. So there's really very little danger there. You're not going to blow a hole through your suit as long as you design the beam spot size correctly. We typically run flux on target at about between 1 and 5 suns, and that's easy to have a suitable suit that you're not going to blow a hole through.
Okay, I'm going to pass it back off to Harri for the panel discussion. And there are a couple other questions which we can follow up with you afterwards if they don't get asked.
Sure. Yeah, feel free to send emails too.
Thank you.
Thank you, Phil. So now we're going to ask questions about all 3 presenters as a panel. So if you have questions in mind that you would like all 3 LuSTR PIs or team members to answer, please submit them through Slido. I'll actually start with one that I know, I think pretty much all of you answered to or addressed to some detail, but since it is important for LuSTR projects to consider infusion beyond the project that you actually have been awarded funding for, the idea has always been that within about 5-year horizon, your technology would be infused to actual mission use. So can you talk a little bit about what your thoughts are in this regard? Where do you see your technology being in 5 years, and have you started seriously considering about how to infuse it into mission use or for commercial applications? Let's start with Paul.
That's a great question, Harry. So we're looking at the construction side of things for the geotechnical piece and for volatile detection on the other end. And so the mining is a little bit further out, but we have been talking and looking for future Eclipse missions. However, our system is fairly large, 1 meter depth, so size of a Viper drill. And so it's not as simple as putting a 1 kilogram payload on it. And so this would be a fairly major mission if we had to include it. And so from a commercial standpoint, we're looking to see, could we apply some of the findings for the geotechnical detection to Earth construction as well. So those are the kind of things we're currently looking at. But we're looking mostly for larger missions in the future to do this one now.
All right, Professor Rahman.
Hi. Yeah. So yeah, I think right now we are working with one industry. So they're helping us in the analysis, and also with the industry we plan for the future Eclipse mission. Recently, also our grant officer, we have talked about that, like discussing with Paragon, who are also developing this cold trap. I believe they also attempted this delamination technique. I saw the video in the YouTube. It's like all the ice, collected ice, were resublimating again. So there is a potential discussion with the Paragon that probably we might help in that thin film delamination techniques in their mission.
Great, thank you. And Professor Lubin?
Yeah, we've been in discussions with Intuitive and others about flight opportunities, because we're at a point where we'd really like to put something on board. Since the system's scalable, a mission could be scaled from really very small to as large as the lander can handle. And it looks like in kind of like the initial landers that we're talking about that can carry a order of, say, 50 kilograms to 100 kilograms of payload, we could easily fit in. I think we can keep our system under 10 kilograms. But again, it's very mission specific. You know, we could do anything from powering a rover to sending power to another asset, this kind of tower of power where you have multiple assets. You know, it really depends on the specifics of the mission, but we'd like to engage in a serious discussion of putting something on the moon soon.
Do you want me to?
Sure.
To send one? Okay. So there was a question that's actually more to you, Harri. Are simulants something that can be budgeted into a LuSTR
Yes.
proposal? Yes. Okay, excellent. Do you have another one you want to do?
Yeah, sure. So I'll ask this question from our PI. So a lot of the efforts that you described have used resources that and facilities that either you have access to or you have built yourself. So how much of a constraint or an enabler do you think these special facilities or resources that you have access to where in first making up your proposal, but then also actually doing the LuSTR work? So what is the role of these unique facilities in your effort? Do you think you would have similar success if you didn't have access to these resources? Let's start with.
Yeah, facilities. Well, I think if I wouldn't have access to the facilities, it would cost me probably a bigger part of the budget to either create the facilities that I need or go to a place and hire the facility basically to do the testing. And so having the facilities essentially allows me to do more work within the budget in a way. And so, yes, I do think it's very helpful to already have some of these facilities. Now, of course, the LuSTR grant's been very helpful to, increase that capability, and of course, getting a lot of experience as well, because nobody really had a lot of experience moving large quantities of lunar simulant around, for instance. And so, in the process of doing this research, we've built a lot of expertise in the past 2 years that I think without the LuSTR grant we wouldn't have at the moment. So.
All right, Professor Rahman.
So for these facilities, the major thing is doing is the training the future generation students in the cryogenic vacuum environment, how to use them, how to handle this equipment. Design first, like designing a couple of the high pressure facilities for the cryogenic experiments, the heat transfer experiments, multidisciplinaries, like it contains the plasma physics. It contains the heat transfer and also the thermophysical properties. So I think it's just a very like a concrete project that gave our future generation STEM workforce exposure to like this extreme environment expertise.
Thank you, Professor Lubin.
Well, first of all, the LuSTR program has been incredibly helpful in terms of pushing this technology along. As I mentioned, we have a large number of students that now are trained in this technology. That's been very helpful. In terms of how to apply the technology, that I think is something that we'd like to understand the various missions that might want something like this. It does lend itself well to a mobile application where you are going to be moving around. Otherwise, you just run an extension cord out to it and be done with it. Although, as I mentioned at the end, if you look at very long range applications, say, 100 kilometers on the moon, sometimes in our analysis, it's more mass effective to use a beamed energy approach versus wires. But this is an area where there's so many applications of this technology that you really want to think about what is the problem you're trying to solve. And we would like to speak with various users of the technology. The other thing not to be missed is that the availability of high quality heat in addition to electrical is important. And in that sense, we can have much higher efficiency than just the raw conversion to electrical power, because you actually have thermal power as well.
But most of the questions that are left are pertaining to Phil's talk specifically. So maybe we can follow up in and provide those since we're at time. Is that okay?
That sounds great. Thank you. So thanks to all our speakers this session. We really appreciate your work on behalf of LuSTR, and good luck with the rest of these, the time you have on this project. So thanks, everybody.
Thank you.
Thank you all very much. Thank you, Harri, and thank you to the panelists. So we're going to take a break now, but if you have a lightning talk, we're about to, if anyone hasn't been to these meetings before, it's time for some craziness. So we try to run through. We want to give some face time basically to some of the presenters, a subset of the poster presenters. So if you have a lightning talk that you've had chosen, we're going to get you lined up in alphabetical order, and then we go talk through these like 2 minutes each to kind of give the high level take homes for your poster, and then we'll break for the poster session where you can have more in-depth conversations and everyone else can mingle and learn about what the rest of the community is working on. We will also have a poster session going in GatherTown for those online, and that has duplicates in an area of the in-person posters, correct? Yep. And we will go between the online and I think we do one in-person first or online first. I don't know which, the other way around. Okay, so all in person will go, and then we'll do all the virtual ones. But I recommend that everyone stay in here and watch the virtual ones because we'll have access to those posters, and we want to share all the technology with all the people.